Hello and welcome back to Linear Algebra. In today's part 22, we will talk about linear dependence and linear independence. However, of course, before we start with this, I really want to thank all the nice people who support this channel on Steady via PayPal or by other means. Thanks to your support, I am able to make these videos here. And as a bonus, you can download the PDF versions and quizzes for the videos. So let's start with the topic of linear dependence in the vector space R2. So this is the two-dimensional plane, and there the notion is very simple. There we call two vectors collinear if they lie on the same line. In other words, the vector u is just a scaled version of the vector v. So we find a scalar lambda in R such that lambda times v is u. So you see, this is indeed a simple concept, and there u and v would be called collinear. Or another notion that we learned today is that we would call them linearly dependent. Hence you see, it means that both together just define one line and not more. Okay, and then you could ask, what is the similar concept in a higher dimensional space like R3? There I would say, let's now consider three vectors. So we have a u, v and w. And now of course it could happen that these three different vectors lie in the same plane. So similarly to before, they now just define a plane and not more. Hence this is now what we would call coplanar. So in other words, we need to find two scalars. So we have lambda times v plus mu times w. Therefore, what we see is that the vector u can be written as a linear combination out of the vector v and w. However, now it might be simpler to use a linear combination out of all three vectors. This means we bring u to the right hand side as well. This means the scalar in front of u is simply -1. So you see, on the right hand side we have a linear combination with three vectors, which brings us to the zero vector here on the left. And exactly this is now what we can generalize. So we want this notion of linear dependence in our general vector space Rn. And it should also make sense for different numbers of vectors. Hence, to keep it general, let's take k vectors out of Rn. So let's simply call them v1, v2 and so on, where I use an upper index such that you don't get confused with the components of a vector. However, often one assumes that out of the context it should be clear if the index denotes different vectors or just the components of a vector. Therefore, maybe at some point in this series we will also stop using upper indices. Okay, but at least for this definition, let's keep it this way. Then, in the next step here, let's put all these vectors here into a set or into an ordered tuple. Either way, we simply call it a family. Now, often it's important that we have an ordered list of vectors, but sometimes also an unordered list will do it. Hence this means most of the time we use the tuple notation on the left, but sometimes we also talk about sets. Okay, and now this family here is called linearly dependent if we find a non-trivial linear combination for the zero vector. More precisely, this means we have a linear combination like this above, where the coefficients are not just zeros. Of course, with zeros this would not be exciting at all, because there it would always be possible to get to zero. Hence, what we need are k real numbers, lambda 1, lambda 2 and so on. Now, some of them could be zero, but the important thing is not all of them are zero. And then we want to have our linear combination like above. Therefore, now we are able to use the sum symbol to write it down. So we start with j is equal to 1 and go to k. And then we have lambda j times the vector vj. So this is a well-defined linear combination and it should get us to the zero vector in Rn. So you see, linear dependent just means that we have a loop of vectors that brings us back to the start. Or in other words, it means that some vectors can be described by the other ones. Okay, now by having this definition, you might already know what it means when we talk about linearly independent vectors. Or more precisely, we should say that a family of vectors is linearly independent. Of course, it simply means that such a non-trivial linear combination for the zero vector is not possible. And indeed, this will be the important notion for a lot of topics later. Therefore, it's useful, instead of saying that the family is not linearly dependent, to put this into a separate formula. So we simply take an arbitrary linear combination for the zero vector, consisting of our k vectors v1, v2 and so on. And then we conclude that the only possibility is that all the scalars are zero. Hence, only the trivial linear combination is possible here. Of course, there you know, if we scale all the vectors by 0, we stay at the zero vector. However, now this property here defines the important concept of linearly independent vectors. And indeed, they will play a crucial role later. But first, I would say, let's look at examples in the next video. So let's meet there and see you soon. Bye!